Okay, let us take the first problem. So we have an aluminium alloy whose K1C value is given to you. Remember, K1C is the fracture toughness, which is a material property given in units of MPa root meter. It's important to note the unit. And it has a yield stress of 400 MPa. And you have a plate of this material subjected to a tensile stress of sigma naught equal to 200 MPa. Okay, so you have this plate and you have a tensile stress which is sigma naught equal to 200 MPa applied on it. Now, obviously, uh, this is safe from yield point of view because the stress everywhere is going to be 200 MPa and the yield stress is 400 MPa, so this is obviously safe. Now, is this safe from a fracture point of view as well? To do that, to figure that out, what we have to do is we have to assume that we have a crack somewhere, let's say in the middle, where this crack length is 2a, this is w. Since no information about w is given, let's assume that this crack is very small compared to the size of the plate, which is a is much smaller than w. In that case, let's we know the answer to this. This is a Griffith crack. So we know what is the stress intensity factor of this particular crack. We know that it is the stress intensity factor, mode 1 stress intensity factor is sigma naught root pi a for this case. This we have already derived, but we can still go back to the tables, and the case that matches this is this one, where if a by w tends to 0, then this tends to p bw. b is the b is the thickness of this specimen. So if the specimen is like this is b. So this is basically the area of cross section of this, and P by BW is sigma naught. So this is sigma naught root pi a, provided a by w tends to 0. So the crack is very small compared to the width of the specimen. So the crack is basically in an infinite plate. That's why you get sigma naught root pi a as the stress intensity factor. Otherwise, you would have to consider this this geometric correction. Okay, so now we take this stress intensity factor and calculate the a that would be needed to attain the fracture toughness. So K1 has to be equal to K1C, and what is the A when K1 is equal to K1C, given that sigma naught is 200 MPa. So if you do that, you get 28.6 millimeter. A is equal to 28.6 millimeter. 2A therefore is 2 into this, that is like 57.2 millimeters is the crack length. So if your inspection process can detect a crack of this size, detect a crack of 57 millimeter, which is quite a large size actually. If it can detect a crack of 57 millimeters, then this design is safe. If it cannot detect a crack of 57 millimeters, then the design is unsafe. It is safe um, from the yield point of view, but from the fracture point of view, it's safe provided you can detect a crack of size 57.2 millimeter. Now you might ask, the crack, why did I assume the crack to be here? I could have assumed it to be here. Yes. So in that case, you will have to go back to the table. So if this is a crack of length A, this is the flaw that I assume that the plate has. So if I go back to my table, this is an edge notched specimen. This is an edge notched specimen. Again, I assume that W is much bigger than A. So A by W tends to 0, and then this this tends to something. A by W is 0, then you have to see what this tends to, and uh, you can again recalculate. You can again recalculate the size A that would be needed for the material to reach K1 equal to K1C, to reach the fracture toughness, and recalculate the A that is needed to reach the fracture toughness for an edge crack. If that turns out to be smaller than this, then that is the critical crack location that you have. Okay, so for the assumption that the crack is here and is of length 2a, your inspection procedure should be able to detect a crack of at least 57.2 millimeters in size. So that's the idea of this problem, that you you know how to design on the basis of yield. This is how you design on the basis of fracture. So to do that, you need to know the K1C of the material. This has to be measured and given to you, and then you can do calculations of this sort and figure out what is the size of the crack that you can tolerate in the material. What is the flaw tolerance of this material? Okay. So now let us look at a, a qualitative picture of a plate that is stiffened. Okay, so this is how the situation is. So this is a plate, an infinite plate. Maybe it is subjected to sigma infinity. Actually the plate is long. It's here, and it is also on this other side, and at intervals of 2b it is stiffened by some strong stiffer members. So this is 2b and this is 2b, and we consider only one period of this stiffened plate and qualitatively try to see how these stiffeners can help in arresting a crack. Now, let me rub this off. Now, for this problem, which is a Griffith problem, if B was very large compared to 2A, then this crack here does not know that the stiffeners are there. B is very far away. The crack doesn't interact with the stiffeners. In that case, K1 is sigma infinity root pi A. We know that. This is, if not, if this crack tips are interacting with the boundaries, then there's a factor Y, which is a geometric factor that comes in. The problem is similar to what we have here. This factor comes in. This factor is what we are calling Y now. This factor comes in when the crack is interacting with the edges of the specimen. Okay, now if y is equal to 1, that means 2b is much larger than 2a, then the stress intensity factor, the stress intensity factor is y times sigma infinity root pi a. So y is a function of the geometry. Okay, now for a unstiffened plate, when a by b tends to 0, for an unstiffened plate, as a by b, uh, if these stiffeners were not there, if these were not there, then it's basically an infinite plate, and this 2a is always very small compared to the width of the plate. So y is effectively equal to 1 if stiffeners are not there, and that's what is shown here. Y is effectively equal to 1 for unstiffened plate. So this is for unstiffened. Now when the stiffeners are there, initially when A is very small, when A is very small compared to 2B, the crack does not see the stiffness. So then Y is again equal to 1. But as the crack grows, as the crack becomes longer and comes closer and closer to the stiffness, it starts feeling the stiffening effect of the stiffness, and the value of Y keeps on dropping, which means that the effective stress intensity factor for a stiffened crack is expected to be lower than that of an unstiffened crack. So an unstiffened crack, Y remains equal to 1, and in this case Y drops, which means that the K1 that you get for a stiffened plate will keep on dropping. So this is kind of qualitative argument saying that a stiffened plate will actually actually apply some kind of resisting force to the crack, and make it difficult for it to propagate. So if K1 drops because Y drops, then to reach K1C you will have to increase sigma infinity even higher. Okay, so for the stiffened plate you will have to use more sigma infinity in order to make the crack propagate than for an unstiffened plate. That's what this diagram qualitatively says. Now what is the effect of this qualitative picture? The effect of this qualitative picture is shown here, where we have plotted a by b versus what is known as the residual strength. The residual strength is the value of sigma infinity, that you need in order to uh, reach K1C for a crack of length A. So we are not using A, we are using A by B, the crack length with respect to the stiffness spacing. That's what we are using. So for a given value of A by B, the sigma infinity that you need in order for K1 to attain the fracture toughness of the material is the residual strength of the material. Obviously, as you increase A by B, the residual strength keeps on dropping because you have a longer and longer crack, and your K1 reaches K1C easily. So for an unstiffened plate, the residual strength drops like this with A by B. Longer the crack, lesser is the residual strength, lesser is the sigma infinity at which it will start to propagate. Okay. Now for the stiffened crack, it will be similar. In the beginning, when A by B is very small. Then the crack again does not see the stiffness, so it behaves as if it is in an infinite plate. So it will behave in exactly the same manner as the unstiffened crack. But then at some point of time, uh, this it will start feeling the stiffness, and that's when the Y starts to drop. So K1C is lower than for the unstiffened plate. For some length of crack, when it starts seeing the stiffness, K1 is lower than for the unstiffened plate, and therefore you have to increase sigma infinity more in order to reach K1C, which means that now the residual strength of the stiffened plate starts becoming higher than that for the unstiffened plate. Okay, then the crack slowly, as you increase the length of the crack, it comes very close to the stiffness. And then it has it cannot break through the stiffeners because the stiffeners are thicker than the plate itself. So it starts feeling the stiffeners very strongly when the residual strength uh, increases even more from the unstiffened case, because the crack is very close to the stiffeners and the stiffeners tend to stop it. This continues for some crack length till a time comes when the stiffener itself is broken by the crack. You have increased sigma infinity so much that the stiffeners break, and then of course the crack will propagate catastrophically, and uh, your residual strength drops again. So this is qualitatively the shape of the residual strength versus A by B curve for the stiffened plate. Now this has consequences. The consequences are, if the crack is very small, so this is a small crack, and this is your residual strength, sigma 1 is your residual strength, then if you reach this residual strength and you try to increase your residual strength, your crack length will increase catastrophically, because there's no part of the curve in here. So the only way for the crack to respond to a stress equal to or slightly higher than sigma 1 is to just keep growing catastrophically. So catastrophic crack growth will result for very short cracks. For very um, longer cracks, say a crack length of A3B, what will happen is, for the unstiffened case, this is the residual strength. This is the residual strength. Again, if you breach this residual strength, then the crack just keeps growing catastrophically. There's nothing to stop it. But if it is a stiffened plate and this is the crack length, then this is the residual strength. If it starts to grow, it will grow catastrophically. It will grow very fast. But then when it reaches this crack length, as it grows, if when it reaches this crack length, it again reaches a residual strength, and now it will stop growing because its residual strength is now higher, is actually equal to the sigma infinity that you have applied at this stage. So this is the mechanism of crack arrest, where a crack starts to grow but then is stopped because the residual strength diagram has an upturn, has an upturn in its um, upturn when plotted against A by B. So this is the limiting crack length. This is the limiting crack length. This one is the limiting crack length. Sigma 2 is the limiting residual stress, at which you will exactly get two solutions to the crack length. These are the two solutions to the crack length. This is below any crack length larger than A to B will, up to this point, larger than A to B to this point, any crack length in this region for the stiffened plate will lead to arrest of the crack. It will start to grow, but then the residual strength rises again as it reaches close to the stiffness, and then it will stop. Okay, so this is the mechanism of crack arrest, and then let's go to the next problem. I'll do that in the next round of